Hello everyone. Today we will discuss electric dipole when placed in an uniform electric fields. So when we put an electric dipole in uniform electric fields, there would be forces on the two charges, minus q and plus q, and there will be also torque. So we have to find out what will be the torque and what will be the net force on the dipoles. And another case, when we put a dipoles in non-uniform electric fields, what will be the net force on the electric dipoles and what will be the torque. Let us discuss first case, electric dipoles. When electric dipole placed in uniform electric fields, तो ये हमारे पास यूनिफॉर्म इलेक्ट्रिक फील्ड्स लेफ्ट टू राइट direction of uniform electric fields, and there is a two charges at place, a minus q at the point of A and plus q at the point of B. So two equal and opposite charge will make an electric dipoles, and we have force on plus B. Force on plus B will be along this ones in the directions of electric fields, and force on minus A will be along these directions. So these are the two equal and opposite forces, and they also parallel to anti-parallel to each other. So they will make a torque. So net force, we will look here, net force on the dipole. On the dipole is equal to 0 because plus q is along this one and minus q along this one. These are two equal and opposite force. Plus QE minus QE. So this become QE minus QE. QE minus QE. It comes out 0. Now this is a dipole axis from minus q to plus q. Dipole moment axis along this ones, and we already know that dipole moment is equal to q times of AB. If I say that the distance between A and B is twice A, then the dipole moment becomes, we represent it vector P q twice A vector. So twice A vector's direction is from minus q to plus q. So now here when two equal force, this and this, and in opposite directions, acting on a system, the systems will rotate. So the system will rotate. The tendency of these two forces are to rotate this dipole in clockwise directions. Since the axis of the dipole making an angle theta with the electric fields, therefore our electric fields is a uniform, which is left to right, and we know that torque means, torque is also known as moment of force. Moment of a force will be torque. So here the magnitude of either these two forces are equal. So therefore the magnitude of either either force multiplied the distance, perpendicular distance between these two forces. So this is the line of action of this force, and this is the line of action of this force, and the perpendicular distance between them will be am. So perpendicular distance between the force. Now the magnitude of either force is a QA. Take is QA the magnitude of either force multiplications the perpendicular distance between these two forces. This is A arm. Now from the triangle AM can be calculated from the triangles AMB. From the triangle AMB, this is angle theta because this is uniform electric fields. Therefore, these field lines will be parallel to each other and equidistant. So this is angle theta. This will be also angle theta. From this triangles, length of AB is twice A. If we need this one, so AM, so therefore sin theta. From here, sin theta is equal to AM divided by AB. So since the length of this dipole is twice A, therefore AM divided by twice A. From here we can calculate AM is equal to twice A sin theta. Therefore our value of torque we represent is by tau. QE times of AM is equal to twice A sin theta. Twice A sin theta. And from the dipole moment, from the expression of dipole moment, Q times of twice A will be the dipole moment. Now this can be represented at this one's 2 QUA times of sin theta, E sin theta. E sin theta. Now this becomes P sin theta. So P sin theta will be the torque or moment of a force. This is the magnitude. In vector format it will be. Now in vector format torque will be P cross C, because dipole moment and electric both are vector quantity. Now the direction of torque P cross C if I found by the right hand rules. So direction will be P cross C. So direction will be inward. In this figures, the direction of the fade will be direction. Its direction will be inward normal to the whiteboard, inward normal. Inward normal generally represented by inward normal to this plane. We represent it by cross. Cross means normal inward, direction will be inward normal. So now there are two cases will appear here. Case number 1. Case first. So the torque will be zero at two position at theta equal to 0 and 0 or pi. The torque will be 0. Torque is equal to 0. And second case, maximum torque will be at case number 2. Maximum torque would be at when theta is equal to 90 degree. We know that sin 90 is equal to 0. Therefore the maximum moment of force will be P. So this is the maximum value. And one important thing for there are two position. One is a stable equilibrium and unstable equilibrium. If I discuss it for a stable equilibrium, unstable equilibrium, then it would be now in a stable equilibrium. Stable equilibrium of the dipole. So when theta is equal to 0, uh, when theta is equal to 0 in these positions, electric field, when the electric field is parallel to the dipole moment, in that case your torque will be at this point, torque will be 0. Torque is equal to 0 and both are in the same direction. It means that dipole moment is the direction of dipole moment along this one, electric along this one. When both are aligned the same direction, it means that one electric field and P is the same direction, then we say that the dipole is in a stable equilibrium. Second case, unstable equilibrium. In unstable equilibrium, if you displace the dipoles from this position, suppose it is the direction of dipole along the electric fields. If you displace the electric dipoles from this equilibrium positions, and suppose if I rotate anti-clockwise then left it, so it will again come in this equilibrium position. So that's why it is called stable equilibrium. Second part is unstable equilibrium. Unstable equilibrium. Now in unstable equilibriums, both the cases dipole in the dipole total torque should be 0, and for unstable equilibrium the condition is theta is equal to pi, and when theta is equal to pi, we know that sine pi equal to 0, therefore torque will be 0. So for the both the cases your torque should be, torque here is also 0, torque in that case is also 0. So torque is equal to 0, but this is unless you disturb this dipoles, it will remain in the same position. It means that your electric field is along this one. So here your electric field is from left to right. Let us suppose your electric field is along this one and your dipole moment is along this one. So minus q and plus q, and dipole moment has the directions. Yes, they are anti-parallel, just anti-parallel. So if you displace the dipoles from in this position, if I disturb this, either rotating from this either clockwise or anti-clockwise, it will not come again in this position. It will not come. This is the position of the dipoles in unstable equilibrium. If you disturb the dipoles from this position, it will not come again in this position. So it will go in the stable equilibrium position. So in earlier case, in this case in a stable equilibrium position, now in stable equilibrium position your electric field is along this one and your dipole is also along this one. So minus q is here and plus q is here. So dipole moment and E in the same direction. So here that's why when you disturb the dipoles from this position, either if I rotate in anti-clockwise direction, it will come again in the equilibrium position. So these are the two important cases. Later we discuss in the energy cases. In stable equilibrium it should have the minimum energy, minimum potential energy, and in unstable equilibrium should have maximum potential energy. So both will be discussed in later part. So here potential energy, U is the potential energy. So P will be minus PE, minus P which will the negative, and here potential energy in the stable equilibriums will be plus PE. This is the maximum potential energy, and we will use the formula for the potential energy. Potential energy will be P dot E, vector P dot E minus P dot. This is the formula of the potential energy. We will discuss this in a later part. So now that's all of this electric dipoles and uniform electric fields. Second case, if the electric field not uniforms, and uniform means either the direction is varying or the magnitude varying. In that case, total net there would be torque is also there, and there will be net force on that case will not be zero. In that case, there would be some net force in the case of when the dipole is placed in non-uniform electric fields.